Supervisor, but I want to read that.
All right. So are there any questions about the homework I posted last week? At least not yet. Okay. So today and pretty much throughout the rest of the entire class, we're going to be looking at different types of what's called regression methods. We're going to spend some time dealing with linear regression models, and we should get time to do logistic regression and hopefully a little bit of forecasting, which is part of the way we're going to do it anyway, is going to be more linear regression. A couple of the things that happen when we're dealing with a regression model, especially if we're dealing with one that we call linear, uh, we're going to have y and essentially be starting off with y equals mx plus b. Pretty sure everyone here has seen this before. So when we're looking at this type of a model, because it is the most basic version of a regression model we can have, we'll actually call this and refer to this as simple linear regression. We can, of course, take that up a little notch if we need to. Ax squared plus bx plus c. Again, everyone here had better have seen something like this before. Most of the time when you see a model like that, you are trying to factor it to solve for values of x that will make y equal to 0. We're not going to be doing any of that sort of stuff here. But again, even though this has a quadratic term, we're still actually going to call that a simple linear regression. What we're going to build up to eventually is we're going to have y equals beta 0 plus beta 1, x1 plus beta 2, x2 plus say beta 3, x3 plus, and then we can keep going. At some point, we can get into beta, I don't know, then say x1 squared plus beta something else, x2 squared, and so on. Once we start looking at a model like this, we start to call this a multiple linear regression. And one of the things that happens when we start dealing with models like these, we can actually start to take into account, say, what are all the differences. So, for example, if we were talking about a two-sample t-test, one of the assumptions behind that is that the only difference between the two groups you're looking at is the one thing you're testing for. Is that ever true? Absolutely not. Do we hope that it's usually close enough so that it doesn't really matter? That is one of the basic assumptions. But with something like this, what we can do is we can take into account a lot of other variables that just aren't part of the original model. So if I wanted to look at, uh, say, student scores on a certain type of an exam, I could take into account, say, what is their gender, what school district did they go to, do they get a free lunch at the school that they're at? Do they have a TI-84 graphing calculator before they take their math class or their math exams and stuff like that? And these beta values, if we're talking about, or if we're talking statistics, those are called coefficients. If you talk with someone that does machine learning or data science or something like that, they're going to call those weights, and weight as WEIGHT. And essentially, the bigger these values are, assuming that they are statistically significant, uh, the more of an impact whatever these particular variables have on whatever the outcome is you're looking for. If we're talking statistics, all of these X values that we have here are what we would call a random variable or an independent variable. The thing that we're trying to model here, so the Y would be called the dependent variable. If you're doing machine learning, if you're doing data science, the X1, the X2, X3, and all that, they call those features. Why did they decide to rename them? Because they took their one stats class, thought that was enough, and then literally started inventing terms that already existed and just made them their own. They're actually serious about that. And then uh, for the Y, you can think of that as an output variable, and you can think of the X1, X2, X3. You can also think of those as, say, input variables. Going to be honest, in statistics, since we call these in X1, X2, X3 independent variables, why do we call it or call them that? It's because basically tradition. One of the big issues that we're going to run into, something we're going to talk a lot about, is what happens if X1, X2, X3 are not independent of each other. That can really mess up a regression model. So even by using statistics terminology and definitions, should we really be referring to these as independent variables? No. But that's what we do, even though it's not the appropriate thing. So if we're talking about a simple linear uh, regression or simple linear model, simple linear regression, how many of you remember in your previous algebra classes having to find or determine what is the slope? And then you have your entire formula and you go and you figure it out. Uh, with what we're going to be doing here, those formulas that you had to memorize for your algebra class, you can forget them. They do not apply here. The idea behind it applies, but the actual formulas that you were given, they actually don't apply. Part of the reason for that is when you were in your Algebra 1 class, one of the things that would happen is you'd have a couple of ordered pairs, meaning you'd have an X value and a Y value, and then you'd have another X value and a Y value. And then you could go in and calculate M uh, and calculate it as the change in Y divided by the change in X, or rise over run, or however you want it to required to memorize it. Here, you can have hundreds of values of X's and hundreds of corresponding values of Y, which means if you're to go in and take every single pair, uh, you'd be trying to figure out what M is for quite a while, and it's just not going to work out that well. Um, with linear regressions, same assumptions as we had before. We assume that in this case, all the different X values are going to be independent of each other. Uh, when we look at a couple of the forecasting models, that's not exactly going to be true, but we can still use or pretend that they are for a moment and actually try to come up with something that should be fairly useful. So for those of you that are getting into finance, uh, trying to predict, say, what is the stock price going to be tomorrow so you can determine whether or not you want to try to short it today, we will actually get into some of that stuff a little bit. There is a new class that's being offered by the department next semester. I believe it's applied forecasting with Python. You get into this forecasting stuff a whole lot more in there, and you do use a whole lot better methods than we're going to be using here. But you can hold off until that. With all of these as well, we're going to be doing hypothesis tests. And for everything that we're looking at, our null hypothesis, if we're talking about just a simple linear regression here, it's basically that m is going to be equal to 0, and then that b is going to be equal to 0. Our alternative is almost always going to be they are not equal to 0. And sometimes with some of the data that I've used in the past, you find that m is not equal to 0, but you'll find that b is equal to 0. So we need to work with stuff like that. We also need to make sure when we're talking about two sample t-tests, when we're talking about ANOVA, there's an assumption that the data is normally distributed. In this case, the assumption is that something called a residual is normally distributed. If we look at the formula for a residual, the way that we're going to be using it, so I'm going to call this residual and then say sub I. It's going to be the difference between what is the expected value of when you plug, say, certain value of x into your regression model minus yi. So this is the actual data point. And this over here is going to be the predicted value. And because you all totally remember everything from your DS 301 class, especially the first week of your class, you all remember for trying to calculate what is the standard deviation. You have this sum of xi minus x bar squared over n minus 1. Well, this stuff that's in the center here is basically just that residual. So if we're trying to create a really good model, one of the things we want to do is try to come up with a model where the predicted value, when I put in a value of x, is going to be as close to the value of y, whatever that happens to be, as possible. Uh, and with this thing right here, do I expect you to actually memorize that and do anything with it? Absolutely not. Part of the reason is if I give you something simple, like say y equals 3x minus 4, and I give you a whole bunch of values of x, can you calculate the expected value you should get for y at all those points. Yeah. But one of the things that we're actually going to look at is when you have one of these multiple linear regressions, you might have 50 or 60 different variables or 50 or 60 different features that you need to go through. And you need to tell whether or not they're statistically significant. If they are statistically significant, you can keep them uh, in your model. If they are not statistically significant, we assume that whatever these beta values are is going to be equal to zero. Zero times anything is zero, so you can get rid of them. So sometimes you can be looking at a data set, just as an example, uh, looking at data set based on 130,000 vehicles, trying to predict whether or not a vehicle is going to come back in for warranty work, based upon, look, if we think about it as a Excel spreadsheet, 80 different columns of data. So use those 80 different columns of data to predict whether or not a vehicle is going to come in for warranty repair. Go. So there's going to be a lot of stuff where uh, the value of X, or the input variable that we're looking at, has absolutely nothing to do with the output variable. Since it doesn't have, or since it doesn't matter, you can actually just get rid of it. Make it easy. I know uh, there are a lot of different statistical methods. If you take the data science class next semester, where they're actually going to try to tell you to keep everything in there because blah, blah, blah. Um, if you do a good job, you can eliminate most of that stuff, so you don't even need to use those advanced methods. So something to look forward to. If we're looking at some of these, or so again, some of the assumptions here. One, residuals follow the normal distribution of some kind. Two, variance is equal. So usually it's the variance at the low end is about the same as the variance at the higher end. We'll see what that uh, looks like in a moment, or talk about that in a moment. Three, again, the data has to be independent of each other. And then four, we assume that there's a relationship between all the x values versus whatever the y value is. And if we're going to be talking about simple linear regression, multiple linear regression, we also have to assume that y is continuous. And for y to be continuous in this case, you have to be able to have decimals in there. If we're doing a model, like I was talking about, where I'm trying to predict, does the vehicle come back for warranty repair, yes or no? Y is dichotomous. In that case, we use something called logistic regression. If y is a count variable, for example, how many points is a person going to score in a game? How many sick days is a person going to take in a year? Uh, that sort of thing. There's actually a whole other type of regression that we're not going to talk about. But in that case, it's actually um, something called a Poisson regression, or depending on what the data actually looks like, there's probably 2 or 3 dozen other types of regression models we could use there. It's, it's not anything that we have to worry about here. Uh, but for what we're going to be talking about for the next couple of weeks, we assume that y is continuous. So again, y is going to have decimal values. We can Those values can be positive, they can be negative. So if we're looking at uh, say putting a whole bunch of people on some sort of a uh, diet and exercise regimen, it's possible that some people are going to lose some weight if they start on there. It's also possible that some people are going to gain some weight, even though they are strictly relying on the this new diet and say exercise regimen. In a case like that, it'd be possible that someone's actually just putting on a whole lot of muscle. So we can look at y and think of that as a change in weight. And then we can look at all these other different variables to see who this exercise regimen helps out the most. So if we wanted to, we could look at it. Uh, some of the variables we could look at in here would be like, say, what type of cardio did you do? So if you're talking about running, did you run on a track? Did you run outside? Did you run on a treadmill? If you ran on a treadmill, how fast did you run? Depending on the type of treadmill that you have. Does anyone else notice that there are many different types of treadmills out there? Or is anyone actually familiar with that? Okay. So you can look at how fast you ran. Did you put an incline on the treadmill while you were running? How fast did you go? Uh, if we're looking at, say, weight training, what types of exercises did you do? We can also use data like this to try to predict whether or not how much you're going to spend when you go to a grocery store or go shopping online or something like that. Uh, we can use the independent variables to do a lot of other stuff too, if you want to get into marketing, but that's way beyond what we're going to talk about in here. So with all this stuff, one of the things that we end up looking at, and one of the measures we use to figure out whether or not we should actually be rejecting or failing to reject the null hypothesis. So I'm assuming here y equals beta 0 plus beta 1 x1. So beta 0 is equal to 0. Then beta 1 is equal to 0 versus 1 or both of them are not equal to 0. One of the ways we can test this is through correlation. And if you've done anything with a correlation before in stats, we usually refer to correlation as a lowercase r. And when we talk about correlation, most of the time, we're actually going to be talking about a linear correlation. So if I've got some data, and let's say I plot it, and my data ends up looking like that, I can draw a regression line through there. And the R value that I'm going to get here going to be positive as well as being large, at least as far as R goes. The values we can have for R go from -1 to a +1. If you have -1, it's a perfect correlation, and it's actually going to be sloping down. If it's a +1, it's a perfect correlation and it's going to be sloping up. So if I had data like this, because it's going up, I'm going to assume that it's positive, and then large based on what we have here. So it wouldn't surprise me if we looked at data like this and found that R was like, say, equal to 0.9 or something larger than that. If we have data that does something like that, I can still go and try to put a model to this, but I'm going to be honest, if you look at the data, you can see that it's kind of sweeping up like that. But I can still put a linear model on here and get something like that. R is still going to be positive, and in this case, still going to be large, uh, within the range of values that I've got here. But the data in this case are not linear. This could be exponential. This could be quadratic. There are all sorts of things that could be going on here to make it look like that. But when you start using the software to figure these things out, the software just looks at the data and fits a linear model to it, and then tells you here it is, here are some of the metrics for determining how good of a model it is. And then it's going to be up to you to decide, is that good enough? If we're talking about data science and machine learning and stuff like that, they will actually never bother to learn or look at uh, the data like this. So they'll never know, hey, maybe there should be an extra term in here to help us get some of that quadratic effect or some of this exponential growth that's going on here. In this class, we are actually going to be looking at that. Uh, I will admit, though, if you've got 2 or 3 variables to look at, it's not that bad. When you've got 80, 100, 200, 500, 1,000, I'm not going to look at all of them either. Just to be honest. Uh, but it is important that we understand that with the data and what the software is actually doing, it's continuously testing. Is there some sort of a linear effect going on here? That also means that if we have data that does say something like that. Does anyone see a pattern there? Yeah. But when we plug in our or use our linear model to try and figure out what's going on, it's going to tell us that there's basically no correlation there because it's looking for a linear correlation, and what we have is basically quadratic. If I give you a data set and I say so 9410149, the correlation between those, the X column and the Y column, is going to be 0. Does anyone see a relationship that's actually going on there? -3 equals f of -3 magically becomes 9. f of positive 3, which is what this guy is supposed to be down here, also becomes 9. What am I doing? Y equals x squared. But even though there is something we can model there, even though there is no variability in the data, if you go in and you use the standard correlation test, it's going to come up that there's 0, meaning that there's no linear uh, relationship between x and y. And a lot of times, if you have something come out like that, you're going to end up with uh, they're assuming that there is no relationship between x and y. And in this case, as well as in this case up here, clearly there is. So one of the things we can do to get around that is we can look at something called, or that's written out as a capital R squared. What you have here is capital R squared is usually just that lowercase r for the correlation coefficient. We square that. But we can also look at it in terms of an ANOVA table. And once we start using this r squared term instead of r, if we do a good enough job modeling our data, we're going to find really quickly that we actually like this r squared thing a whole lot better, because it doesn't assume that we're dealing with a linear model. It assumes we're dealing with some type of a model, and some type of a model that we've actually come out and tried to specify. So if when we're dealing with the data, when we put our data into whatever program it is, uh, we need to, or we can go in, we can model it, we can make all sorts of different plots, we can check all of our different assumptions. And like I said, the thing that we want to get into and start using is actually going to be this r squared value. I'm not going to bother showing you uh, the formula that the software is going to use for r squared for two reasons. And the first of which is I don't remember what it is either. So I'm not that worried about it. If we want to open up a mini tab really quickly, it's making me sign in here. So is anyone else tired of having to go through all of this just to use Minitab, or is that just me? So if we're looking at Minitab, I can come in here and I can say X, then I can say Y, and I'm just going to put in the values that I've already selected. And then for the Y values, like I said, that's going to be 9, 4, 1, 0, 1, 4, and then 9. Once we've got our data put in here for C1 and C2, we can go up to Stat, and then Regression, and then Regression. And we're going to look at where it says Fit Regression Model. Some of the nice things that we can do with the mini tab here. And you can see that there's an option on there called best subsets. We'll talk about how we use that a little bit later on. But for right now, I'm just going to say fit regression model. And can go in here and go ahead and click on that. And you can see that we've actually got three different options here. It says responses. So that would be the output variable. That would be the dependent variable. In this case, that's going to be y. Then you can see that there are two other uh, things on there. One says continuous predictors. One says categorical predictors. So with the continuous predictors, we're assuming that those are essentially numeric values. Those can be any type of numeric value we want to deal with. So and they have to be essentially true numeric values. So what am I talking about there? For example, if any of you get into marketing and marketing research, standard practice has been for many, many years to code certain things, such as what is your gender, male or female? And they will code it as, say, 0 is male, 1 is female. Why are they doing it like that? Because if you go back in time, say like 50s, 60s, and 70s, the amount of memory that you have on your cell phone right now, even if you've got the crappiest cell phone that's available, is what, thousands, if not millions of times more than some of the most fanciest uh, uh, like high capacity computers from the 70s. So being able to condense, say, gender and just calling it, say, GEN as a variable name, and then putting in 0 and 1 instead of male and female, that saves you a significant amount of space on your hard drives, which is why they would do it. But when you look at the data, if you're not careful about that, uh, you'll see gen and then 0, 1, 0, 0, 1, 1, 0, 1, whatever. If you put that in as a continuous predictor, not going to work. The software doesn't know any better, so it's still going to give you results, but it's not going to do what you think it is. What you need to do is actually put that in as a categorical predictor. For us, though, we can think of X as being continuous, so I can just go ahead and click on there. When we look at everything that we've got down here, some of this stuff is actually going to be very, very useful. Some of this stuff, not so much. But if you click on model really quickly, uh, depending on software that we're using, a lot of the stuff that we find in here could actually be really useful. For example, we know there's going to be a quadratic effect here. I'm not going to put that in there just yet, so I'm just going to keep everything as is. You can look down here where it says terms in the model and it just says X. So let's go with that. Options. When we're doing this stuff for real, there will be times when the data we have doesn't necessarily fit the assumptions that we were talking about. So we might need to use one of these Box-Cox transformations here. There will be some other times when we want to weight some of the data differently. So you can plug stuff in here. For right now, just click on OK. For coding, We'll actually get into this in a moment. If I leave everything as is, so it says do not standardize, just leave it as is. So I'm going to click on OK for the moment. Stepwise, right now the method we're using is none. And what the stepwise method does is if we have, say, 70 or 80 different variables, we can use the stepwise method to eliminate certain variables to make it easier for us to figure out what is actually going on. For right now, we don't need to worry about that at all. Validation, this is something probably starting 2 Thursdays from today, we'll actually be talking about. For those of you that were at the talk that I gave in the math department, you know that part of your in-class work is going to be analyzing data and then writing your results up on the board. And part of that comes from using these validation methods, where you take the data set that you have, you break it down into smaller chunks, and then things happen. For right now, though, we don't need to worry about that. Storage, uh, we can get fits, residuals, standardized residuals, deleted residuals, leverages, all sorts of stuff here. For the most part, we don't need any of this, but there will be times when we do want to use the residuals. And the fits are just that expected value that I was talking about. What is our predicted value of y at a given value of x? And then graphs, to make it easy, basically we're always going to be using a Pareto. And then down here where it says residual plots, we're always going to want to do the 4 and 1. Just make it easy. We're going to be using this stuff quite regularly. Then I can click on OK. Results. Sometimes there's a little extra checkbox we can put on down here. Sometimes there's stuff in here that we don't really need to worry about. The default setting is usually good enough, so I'm just going to go ahead and click on OK. And then once I've got all of that, come up here and click on OK again. And what has happened here is when we look at the data, what we're trying to do is fit a regression model. So y equals mx plus b through something that is quadratic. If we look at, come on. Okay. So if we look at our coefficients table here, and I should probably be sharing this. You can see the predicted model that we have here is that the constant term, so that b in y equals mx plus b is predicted to be 4. We have a standard error for that coefficient. This is giving us a t-value for that coefficient and also a p-value. This p-value is below that 0.05. So that's telling us that there seems to be a statistically significant term here, which is the constant. When we look at x, it's telling us that the predicted coefficient for x is 0.000. The standard error for that coefficient, 0.775. The p-value is 1, so that's way above 0.05. And this VIF thing that we have out here is something called a variance inflation factor. We want this value to be as low as possible And the lowest value we can actually get with Minitab anyway is going to be 1.0. What's going on here is if some of our variables that we're looking at are actually not independent of each other, this value increases. This variance inflation factor increases the standard error that we have here, which makes it a lot harder to see if there's if one of the variables we're testing is actually statistically significant. Looking down here at model summary, this is telling us that the standard deviation for the model is 4 r squared. So this is our correlation coefficient. Squared is 0.00. R squared adjusted and R squared predicted. Going to use those quite a bit coming up. For right now, don't need to worry about it. Here is our analysis of variance, so our ANOVA table. And this is set up a little bit differently in Minitab than what I was showing you with the ANOVA tables that we were doing last time. But it still comes out to be model versus error and then total. This Pareto chart is an easy way to tell if a variable we're looking at, if it's statistically significant or not. Since there's nothing on here, it's telling us there's nothing statistically significant. And when we get to this stuff here, this is where those assumptions I was talking about with is the data normally distributed? Are the residuals normally distributed? Are the residuals, does there seem to be a pattern or are they independent? So looking at what we have here, uh, do these 4 blocks look like they're making a normal bell-shaped curve? Absolutely not. The normal probability plot, we talked about this a little bit before. Do all the data points seem like they're near the red line that's on there? Yeah, not too bad. But looking at the residuals versus observational order, does anyone see a pattern here? I do. So we can use this to tell, is there uh, some issue with the independence of variables or the residuals compared to the observed order? And then when we look at residuals versus fitted values, we're looking here to see, does there seem to be a pattern? What both of these should look like is just a whole bunch of blue blobs or a whole bunch of blue dots that are just randomly tossed up there. And when we're looking at these, we see that clearly that's not what's going on here. Looking at the data here for residual versus observation order, this is telling me that there's most likely a quadratic term that I need to put in here. So if I want to do that, I can go back to stat, regression, regression, go back to fit regression model again. This time, I can go to model. And here, right now I've got X highlighted. And I apologize for it being so small on here. But you should see something on here that says terms through order. I should be able to take that and up, you know what, I'll up it all the way to the 3rd order just so we can see what's going on. And then I need to click on here, add. And what has just happened is Minitab has automatically added a quadratic term as well as a cubic term to the model. Include constant term in the model. Yeah, that's fine. So now I'm going to click on OK. I'm going to keep everything else as it is and click on OK again. And what happens here is we've got a new table here with coefficients. The t-value and the p-values here are completely starred out. Part of the reason for this is the data I put in here, there is absolutely no variability going or in here at all. And what this is telling me is that the constant, as far as we can tell, is equal to 0. The coefficient for the x that goes out in front of x. So if we're thinking about this in terms of a quadratic model, y equals ax squared plus bx plus c. This is telling me that the value for c is 0. The value for b, again in ax squared plus bx plus c, is also equal to 0. But down here where we've got the quadratic term, so this is our x squared term, it's telling us that the coefficient is equal to 1. So this is telling us when we look at this model that our model should be something like y equals x squared, which is exactly the model that we're using up there. When we look at the r squared value, we can see that the r squared value went from being essentially 0 to 100%, or 1, however we want to look at it, which is cool. The higher this r squared value is, or more accurately, the higher this r squared adjusted value is, the better our model is at handling variability. And then we look down here, because I didn't put any uh, noise or any variance in with the model, we notice that all these things look completely different. We no longer have an issue with the residuals versus observational order looking like a pattern. So something we can do here, just to add a little bit of interest in here. I'm going to change these around a little bit. Keep them close to what they were. But by no means keeping them exactly where they were at. So let's say this is going to be a 1.3. We'll call this a 4.1. And we'll call this, say, 8.8 or something like that. So looking at the data that we have here now, we don't have exact values like we did before. If I was to give you, say, the original values we had here, told you to find uh, a quadratic model that fit the data, you could use those 3 data points, figure out what is A, what is B, what is C. If you have a calculator to do it, that's even better. But what we've done here is we've taken all those values, mixed them up a little bit just so we can see what's going on. So again, I'm going to come back, go to Stat, Regression, Regression, Fit Regression Model. And I'm going to keep everything that I had the same for the moment and go ahead and click on OK. And you can see some of the things have actually changed on here. So if I download this to, sorry, let's try and do this over again. All right. So again, we've got our coefficients here, and this is our coefficient table. And what this is trying to tell us here is that based on the data we have now, trying to get all this stuff on the screen at the same time might be a bit much, but hopefully you can all see what I've got up here well enough for the moment anyway. This is telling me that my model here is going to be y equals 0.131 plus 0.129x plus 0.977 x squared plus, oops, that should be a minus 0.0194 x cubed. With this particular model here, because we're looking at it as a cube, our hypothesis test here is basically that beta 0 equals beta 1 equals beta 2 equals beta 3 equals 0. Our alternative is something up here does not equal 0. Looking at the table that we got from Minitab here. Come on. The p-value here for the constant, for the term in front of x, for the term in front of x cubed, are all well below or well above 0.05. So, based on the data we have, we'd say fail to reject H naught, fail to reject H naught, reject H naught, and fail to reject H naught. So with these, we assume that they all are actually going to be equal to 0. Since 0 times anything is 0, we can actually rewrite this entire model here. And just say that our model for the data that we just looked at is y equals 0.977x squared. Everything else on there, because we can't tell the difference between it and 0, we can eliminate it. And in statistical terms, we'd say this is a full model. Because we eliminated terms that do not belong or are not statistically significant, we can call this the reduced model. Once we have the reduced model, we can then start using that to try to predict what y is going to be based on the values of x that we have. Are the values that we predict for y going to be 100% correct all the time? Absolutely not. But are we going to get something that's pretty close? That is the hope. That is always the hope. Does it always work out that way? Again, absolutely not. If we look at the R squared adjusted value here, 99.77, that's really, really good. These VIF values out here, for the quadratic term, it's 1. For x and x cubed, it's 7.35. Those are a little bit high compared to what we would normally want to deal with. When we look at our Pareto chart here, there's this dashed red line that we see here, and we see that they're calling it AA. Why are they calling it AA? Because it's a predictor, or the predictor we have, and then we're squaring it. So this is a way of looking at the data really quickly, trying to determine, does there seem to be something that is statistically significantly different going on here? Yes, there is. Looking at the data here, do the blue dots seem to be surrounding the red line? For the most part. We've got limited data here, but for the most part, does it look like it's going from low to high in the center, then back down to low on the outside? Yeah. Does anyone see a pattern that happens to be going on here? Maybe a little bit. Does anyone see a pattern that's going on looking at the data down here? Hope not. So what this is telling us is that this model that we just made here is a lot better than what we had before. Is this model that we have absolutely perfect or the best one that we can get? Uh, just because of the way how things are, if we wanted to, we if this was say actual factual data, we could go in, we could start looking at some of these data points, and we could start saying, well, maybe there's something else we need to put in here, or maybe what we've got is a bit too much. So we can adjust our model as needed. If I go back to stat, regression, fit regression model again, and I come down here to say stepwise, and I'm going to click on method and say stepwise. I'm going to leave everything else as it is on here. And then I can just click on OK. What's going to happen is the software is going to look at the variables I've got and try to eliminate variables that do not belong in the model and keep variables that should be in the model based on either it looks like it's statistically significant or uh, there's some things we can do here with hierarchy. I'll get into that a lot more later on. But if I go ahead and click on OK, then click on OK again. What just happened here? It literally eliminated everything. So that could be an issue. Go back to stat, regression, and just so we're honest and clear, is this how you do this if you are a statistician? Yeah. You think this is boring. Wait until you have to do this 150 times in a day to come up with a model. So I'm going to go to coding, change the coding to subtract the mean. Let's see if that helps. And it's again decided that nothing actually belongs in the model. Ugh. Sometimes, uh, if any of you do end up taking the data mining class. One of the things that's going to happen is there's going to be the software you use is generally going to auto select whatever variables it wants, which means it's using something similar to this stepwise regression model. And so far with the data we've got here, we're seeing it might not actually work that well. So I'm going to go back to model, going to eliminate uh, the cubic term because we saw that the cubic term was not statistically significant and it had a high VIF next to it. I'm going to click on OK. Stepwise, going to get rid of that. So sorry about this. Then click on OK. Try this one more time. And looking at what we have here, we've got a slightly different model from what we had before. The VIF for the two terms in here are both 1, which is something that we really want to have. Again, we're looking at the data, and this table is telling us that the coefficient for x, so again, if we're thinking about a quadratic model, y equals ax squared plus bx plus c. This is telling us that the b and the c do not seem to be statistically significant, which means we can remove them, which again is telling us that the model that we should get from all of this is the same one that I wrote down earlier. So y equals 0.9771 times x squared. And in this case, that's going to be the best model that we can do. Looking at the model summary here, R squared adjusted and R squared predicted are both fairly high. That tells me that the model is actually pretty good at trying to predict future outcomes. With a lot of the stuff you do in machine learning, what's one of the things that you want to do? Predict an outcome. This is telling us that it's 98.9% accurate at predicting an outcome. Sounds good to me. Again, look at the ANOVA table, set up the same way as before. So where it says regression here, that's the model that we're dealing with. The stuff that's underneath is just a breakdown of what is x contributing to the model, what is x squared contributing to the model. The error is the error, the total is the total. All the calculations that I had you do for ANOVA still hold up here. Pareto chart is still telling us that x squared seems to be statistically significant based on what we're looking at. The residuals, do the blue dots seem to be up along the red line here? Yeah. Does there seem to be any pattern of data in here? No. Does there seem to be a pattern of data down here? No. Does this look like it's normally distributed? No. But like we talked about before, because we've got small data set, uh, these histograms might not be the best thing to look at the way that they're set up. If I've got a total of 7 data points here, the number of bins I should have here is 2 or 3. This is trying to give me 6. So can actually ignore the histogram in this particular case. But overall, does this model look good? Yeah. Uh, would I be, if we were talking about some production plants or uh, trying to predict what is our next customer going to do based on the data we have here, would I feel comfortable using it? Absolutely. And again, the model, once we get it all done, It's just going to be that 0.9771 times x squared. And we just use that for everything. So if I asked you, well, what happens if a customer comes in and their value of x is 15? You say 15 squared times 0.9771. That's the value I think they're going to have for y. Well, what if a customer has a value of -7, x equals -7? -7 squared times 0.9771. And then you can be done with it. We'll talk a little bit more about how we can use all of these things later on. But for right now, uh, we've got an idea of what to look for and some of the buttons we can push. I will have some actual data for everyone to use on Thursday, so we can actually see what real data looks like. And again, when I say it's real data, I actually mean that it is really real data. One thing I want to say before we head out of here, though, is when we're dealing uh, with our models, a lot of times, uh, and again, depends on the data we're looking for. So if I've got y equals, say, mx plus b, if that m is big, I can usually look at that and say that it will be statistically significant. But there are times when we have to look at what is the value of m, and we might actually find that something is really small. For example, if I've got data, and this actually comes from when I was working as a chemist, trying to create something called a calibration curve. The result that I'm looking at is the area of a triangle, which the software determined was, say, 10 million. Now I've got to find a way to relate that to the concentration of a known standard that I made, say 0.25 molar. Do you need to know chemistry to do this? No. But that's the concentration. That's the response the instrument gave me. What's the value of m going to be here if we look at it this way? In this case, m is going to be 10 million divided by 0.25. So it's actually going to be fairly huge. But what happens when we start using a calibration curve? We get some beta value times the area. That's going to be the concentration. So it's basically this whole thing backwards. So 10 million times the beta is going to be 0.25. What's that beta going to be? 0.25 divided by 10 million. So it's going to be small. It's going to be really small. But just because it's, I think in this case, it's going to be what? 10 to the -5, 10 to the -6. So a whole bunch of zeros followed by a number at the end of it. That doesn't mean we can disregard it. That doesn't mean it's not important. That doesn't mean it's statistically not significant or practically not significant. It just ends up that's how things worked out. So uh, if you're working in a lab of some kind, or if you're working with people that work in a lab, you'll find that a lot of their calibration curves, which are based on y equals mx plus b, the coefficients, the beta values, the slopes that they use will generally be really, really, really small. But just because it's small doesn't mean it's not really, really important. And that's all I've got for today. So on Thursday, I will have a couple different data sets that we can work through and get an idea of how to use the software, how to actually interpret the graphs and plots and all that using real data, and hopefully start getting into multiple linear regression where you can start to do actual useful things.